Well, there's a interesting and perplexing problem with surfaces that we did not have with functions of one variable. And that's that it's possible for f of x equal to 0, partial derivative of f with respect to x to be 0, to show that there's a maximum in the x direction, and f of y, partial of f with respect to y, to be 0, to show a minimum in the y direction. Now, how can it be an x in one direction and a y in the other? How can the partial be show a maximum in one direction and a minimum in the other?
Are you trying to give me the double talk?
I'm not trying to give you the double talk, but I mean, that's a weird thing that happens here that's possible. And when that does happen, then you have a situation that's called a saddle point.
It's all your fault, you.
No, it's not my fault, it's just the way the function turns out. So here's a classic example of a saddle point. A graph of f of xy equals y squared minus x squared will show a saddle point at the origin, and notice the partial with respect to x is 0 there, and the partial with respect to y is 0 there. And here's a picture of it, and you can see that in the y direction we have a maximum. I'm sorry, in the x direction, when we look at it, in this way. Oh, I didn't mean to move it. When we look at it this way, from the x side, right, from the x-axis, it's a maximum. When we look at it across the y-axis, it's a minimum. And right at the point 0, 0, right here, right, x is 0, y is 0, is what's called a saddle point. And that's an interesting occurrence. Never had anything like that in Calculus 1. And so this theorem is, by the way, just as a reminder, in Calculus 1, once you found a critical point, what did you do to determine if it was a maximum or a minimum or neither? One of the tests is called the second derivative test to see its concavity. Well, there's a second partial derivative test to determine whether or not we have a maximum, a minimum, or a saddle point. So here's the story. Let f have continuous second partial derivatives on an open region containing a point AB for which both partial derivatives, both first partials with respect to x and y, are 0 at that point AB. Well, consider the quantity d, and I don't know what to call d, maybe it's the differentiator between which situation we have. But if that's the second partial at AB times the second partial with y, second partial with respect to x at AB times the second partial with respect to y at AB, multiply those two, and then subtract the square of the mixed partial, and examine the sign of this d. If d is a positive number, and the second partial with respect to x is positive, then f has a relative minimum at the point AB. If d is positive and the second partial with respect to x is negative, you can think of that as concave down, then f has a relative maximum at AB. So you think of this one as saying it's concave up in the x direction if you want. And then if d is negative, then the point AB, f of AB, which is lacking the parentheses, there I fixed that, is a saddle point. And if d equals 0, then just like sometimes the second partial derivative test doesn't tell you much in Calculus 1, because the second derivative equals 0, then we don't know anything. Okay. So condition 1 forces both partials to be positive, sort of like concave up in both x and y directions. Similarly, condition 2 means concave down in both directions. So hopefully you understand that. So examine for relative extrema and saddle points and sketch. And that's not something I'm going to require you to do. but since I've got the fancy software, I can show you a picture of this problem. So here's the situation. We've got a function f of xy, x squared plus 6xy plus 10y squared minus 4y plus 4. So the first partial with respect to x, 2x plus 6, partial with respect to y, first partial with respect to y, 6x plus 20y minus 4. Solving simultaneously this set to 0 and this set to 0, we got these two equations then, right? And we get the critical point of x is negative 6, y is 2, and of course if x is negative 6 and y is 2, then we get 0 for z. You want to try that. Negative 6 here is 36. This 36 would be times negative 72 plus 40 minus 8 plus 4, so yeah, it comes out to be 0. You could double check that. So now the second partial is actually pretty easy to do that. Partial of this with respect to x is just 2, because the partial with respect to x of 6y is, well, 6y is a constant, so just 2. Partial with respect to y of the partial already with respect to y, so the second partial with respect to y is just 20. And the mixed partial, either by doing the partial with respect to y of this, we get 6, or the partial with respect to x of this, we get 6. So that partial is 6. So we look at the second partial with respect to x times the second partial with respect to y minus the mixed partial squared. We would get 2 times 20, which is 40, minus 6 squared, so that's positive. And the second partial with respect to x is positive, so we have a relative minimum. And here is the graph. So hard to see it, but at the point x is negative 6, y is 2, z is 0, we do have a minimum point. Let's see if I can find it. X is negative 6, that's back here. Y is 2, and z is 0. And I drew the plane, the xy plane in there. Whoops. So you can kind of see it. I don't know if you can see that this is actually curling up a little bit. Not very much, but curling up a little bit. And if we continue this out further, you'll see it curling up in the other direction as well. So maybe it would look better if I connected up the dots a little bit. I don't know if you can see that it actually touches back somewhere. Well, I should see the point where it touches at negative 6. Right there is a perfect picture of it. At negative 6 and y equals 2, there's just one little dot there where the surface has a minimum. When I move it around, it's hard to tell what will happen, but okay, so we have a minimum point.